Okay, let's start from the current slide. Now, well, we may even turn on the projection today. Y'all can see without it, can't you? Okay. I don't know of any major announcements. We're not quite on 7.2 yet, though that's where we're starting from, because we had the last problem on example 7 and 7.1 to do, and that's what I'm going to try to do on the white part of this one, just so I wouldn't have to stop and start again a different section. So here's what we've got. Prove that the volume of a pyramid with a square base is V is equal to 1/3 HB. That the volume, let me get my pen activated. The volume of a pyramid with a square base, I'm going to put a square there, okay, is equal to 1/3 HB. Okay. Now when you see a capital B like that, that means the area of the base, not that there's some measurement that's B. That wouldn't have enough dimension. That's the area of the base. Okay? And it says it's a square base, so let's let the, well, draw a picture, okay? Now, I don't draw good pictures, okay? And they're going to set this up on the XY coordinate system. There is technically a Z dimension, but we're not going to be using it, okay? So here is approximately our square base. This is not coming out to be a very good square here. That's approximately the square base. And have the probably didn't do that one well because this is three-dimensional. Let's use the picture in the book, not mine. Okay. Okay. Now, if that really were a square base, that each of these, what you want to name the dimension of the side, you get to pick a letter, any letter you want.
M.
Second?
M.
M, okay. So this will be M, that'll be an M, this will be an M, and this will be an M. Okay? But, as you see, we're trying to bisect this with the x-axis, and this is the y-axis up here. And by the way, the height here, that's your h. That's where the h comes from. It's right there. Okay? Now, your vertices here are at, your z-axis is going out here, but it's really immaterial because we're not going to use it. But this bisects everything there. Let me get Corbin. No, huh? Preston, right? Okay. All right. I realize I probably didn't call Davis's name, but he's not here, is he? Just realized I skipped the name there. Oh, this is an ugly, ugly drawing. Use the one in the book. It's a lot better. Okay? Your height is h there. Okay. Oh man, this is so ugly. It's going to be hard to do anything from this. Use the one in the book. Okay? Now, like I said, I've drawn the z-axis in there, but we're really not going to use it because what we're really interested in, and I think I'll go with a different color, hoping this will not be quite as ugly as it looks. Anyone want to pick a color for me? Red? Is that what I heard? Okay. So we'll go with red if I can get red to come up. Okay? So we're going to take some arbitrary square up here. And by the way, if that's a square base, then at any elevation, by the way, obviously what's our d's going to be here? The way I've drawn it. D what? Dx. Oh, this is supposed to be an x, there's a y. So your d's are on the y-axis. That's the thickness of that plate. The measurements here would be along x and z, but we're not really going to use z because it's a square and we could just use x a couple times. So we're doing dy's here, okay? Because this is actually a little thick disc or plate here. And this is really getting uglier and uglier. So this is your dy. There's the delta here. And the y is going from y equals 0 to y equal h. Okay? So we've almost got what we need for our integral. So let's at least set that up. So we're doing an integral from y equals 0 to y equal h. So you know we're going to have a dy here. So that leads that we've got to get your horizontal dimensions in terms of the y. Well, what's going to link the area of this plate? The volume of the plate you're going to get from the dy. We need the area of the plate. Okay? And what's going to be that? Okay? Well, let's take a look here. You know you're starting down here where y'all gave me a dimension m, so the x equal, this is m plus 2, and back here is m minus 2. No, I'm sorry, where did I get 2? This is 1/2 m, and this is minus 1/2 m. Because the whole dimension is m, you're going half a dimension here, half there. Same thing here. This is going to be minus, let's see, which way is z going? Yeah. Minus m over 2, and this is going to plus m over 2. So the whole length of that at the base is going to be m here and m there. Okay. Now, that really doesn't really enter the picture too much here, does it? Well, it does a little bit. Because what we're interested in is that measurement up there. And let's use what the book is using here. Oh, I probably have already blown that. No, haven't. Okay. Now, okay, in the book they're using b as the dimension of the base, where I asked you and you said m. So what we're using is m, they're using is b. So what they were calling b prime, we're going to call m prime. And what m prime is, and this is what's so tedious about these problems. The calculus won't be hard, it's setting up the problem here. Up here, this dimension here, right here, and here, and here, and here are all going to be m prime. Okay? Those are the m prime. Now I'm getting this as ugly as it was before. So you have a little square up there of thickness dy. We got the dy. We got that m prime up there, and of course this is going from m 1/2 m prime minus 1/2 m prime minus 1/2 m prime m prime 1/2 m prime. So the dimensions here are your m primes. What we've got to do is come up with something that relates the m you know. In the book it's the b you know, okay, because you tend to know the base down here. By the way, the area of that base is, let me go back to my dark, area of the base is m squared, right? If you chose the bottom of that to be m by m by m by m, m by m is m squared. So that's the area of the base, okay? Now what, and if you know b, you know m, okay? So let's just assume that's known. You know h. You just don't know what it is, but you know it. That's given in the problem. So what we have to do is talk about these m primes here. So, cause let's go back to the red here. The area of this slab here is going to be, let's stick with, no, okay, we're okay. Okay, that's going to be m prime squared, because its dimension is m prime by m prime, so that's m prime squared. Thickness is dy, so what we're going to have that we're doing is m prime squared. And you're going to be integrating these m prime squared all the way to dy from 0 to h. Okay. Now this is ugly and messy. But we need to figure out what that m prime is in terms of the things we know, m and h. Okay? Now, I'm going to choose the least messy side of this, hopefully so you can see it better. So I'm going to take off this and this, several of those things. Okay, take off this one. Okay, so hopefully it's not quite as congested as before. Okay, now let's do this line here. Okay, it's not quite where I wanted it to be. Well, okay. Okay, and take it over to the midsection and go here. There we have a triangle, don't we? Okay, this side is m over 2, right? From the post in the middle to the edge here is m over 2. That's the same as here or here, wherever. This right here is h minus y, right? H is the total height, and y is the value you've gone up from the base to here. So there's your variable y is this height, and this is your m prime over 2. Okay? Now, that ratio between this and that, and this is h minus y to this, is the same as the ratio of h to m over 2. Do you see that? If you can carry that on down here, that ratio, and let me get back to my dark color. Okay, the ratio of h to m over 2. That's the same ratio as the red one up there that I had highlighted. Oh wait, I think I recognize this guy. Okay. He's been somewhere before, I've seen. Okay. There's Terrell. Okay. Got it. Okay. Are y'all follow? You see that those ratios? Okay. So what we just said was the h we know to the m over 2, should have done it the other way, is the same as y minus h is to m prime over 2. Okay. We're integrating y, okay, so we want to get this, and we're squaring the m squared. So let's solve this for m prime, okay? And that's an ugly, ugly mess right now. And what that gives you is h m prime over 2 is equal to, product of means equal product of extremes, m over 2 times y minus h. Okay? Well, guess what? We can get rid of the 2's right there. Done. Excellent. I'm all in favor. Okay. And we want to get m prime because that's what this area is in terms of the things we know and the variable y. So we almost have it. M prime is equal to m times y minus h divided by h. Right? Okay? Let's square that because that's what our area is, and that's what we're going to put in here. Now, is there any way to make this a little more palatable? Let's rewrite this as my over h minus m. Right? If we multiply this, we get my minus mh divided by h. It's my over h minus mh over h, so that's just 1. So that's a constant. This is a constant. M over h is a constant. And there's your variable y. Okay, so that's sort of a linear form. I like that a little bit better. And now let's square that. Okay, because we're squaring our m prime up here, and that's what m prime is. So that'll be m squared over h squared y squared minus 2 m squared over h plus m squared. Right? Actually, why don't I have the m on the outside anyway? So let's put the m squared out here. We don't need it in there anyway. And then what we have is 1 over h squared y squared minus 2 over h plus 1. If I pull out the m squareds there, I think that's what we got. Do y'all agree with that or not? You okay with it? I'll hold you to that then. Okay. All right. Now let's differentiate that. Oh, wait. I left off a y here and a y here. When you do the cross product, you get a y in there too. Okay, so it'll be m squared, antiderivative of 1 over h squared y squared. What would that be? Help me. Antiderivative of 1 over h squared y squared. H is a constant, remember. Y is your variable. Antiderivative of that. Second? That's the derivative. Said the antiderivative. Help me. I'm drowning here. Y cubed over 3h squared. Right? Okay. Minus y squared over, the 2, I'm going to get rid of that and just leave it y over h. Okay. Plus the hard one. Second. Antiderivative of 1 dy. Why? Why not? Okay. So we'll do this from 0 to h. Okay? Now, And this is what we're plugging in for the y's, the h. I'll do the 0 part. Done. Okay? So we have an m squared. And by the way, m squared is b, isn't it? Right here. So let's just make that capital B times, and when you plug in an h for the y, that would give you h cubed over h squared, which would be 1/3 h, right, minus h squared over h would be h, right, plus h. H minus h is 0. And what do you get? 1/3 BH, or HB. And that's exactly what we got up here. Wasn't that fun? Okay. Usually a lot nicer to do with numbers, but if you're careful with your variables and constants and things like this, you can make it work too. Now, they don't show that on the slide, so I'll let you handle it. They did it slightly differently from what I did. It works okay. What's that? That's page 460 in the book. So they did it slightly differently, but it worked out the same way. Okay? Now, I think I already gave you most of the homework exercises in 7.2, but just to do them again, either 5 or 7 or both. Both of those are at calcchat.com. 5 is at calcview.com. 9 or 11 or both. Both are at calcchat. 9's at calcview. Either 13 or 15. Both are at calcchat. 13's at calcview. Either 17 or 19 or both. They're both at calcchat. 17's at calcview. Either 21 or 23 or both. They're both at calcchat. 23's at calcview. Any of the odds 25 to 31, they're all at calcchat, and none of those are at calcview. Either 33 or 35 or both, they're at calcchat, neither are at calcview. Either 37 or 39 or both, they're both at calcchat, 37's at calcview. Any of the odds 41 to 47, they're all at calcchat, none of them at calcview. Either 49 or 51, they're both at calcchat, neither are at calcview. You can try 53 if you'd like. It's a little bit deeper and more involved, as is 55, though it's not too bad. But these you just decide whether you want to go a little bit deeper or not. Let's see, do 57 if you can. That shouldn't be too bad. And then any of the odds 59 through 69. Okay, there's several there. Choose any or all of it. Well, actually, yeah, do that. Then there's a think about it at 71. You can certainly do that. You don't have to do 72. The only reason I mention it, look, there's a name there, Cavaleria's theorem. So if you wanted to choose to write on him, that's fine, or how he developed his theorem, or what difference his theorem makes, anything like that, you could write on that. 73 and 75 you can certainly do those. Those get to be pretty, a little bit more complicated problems, but you can give them a shot if you'd like. And 77, again, is a little bit more complicated, but you can certainly try that if you'd like. So let's move on to 7.2. Whoa. How did I get 7.2 here? I hit the wrong key all this time. Yuck. I'm supposed to be in 7.3, and I must have, I think I clicked on it, but my cursor must have moved when I did the second click and got me 7.2 again. I don't know. But anyway, here we go again. Now we have to wait for PowerPoint to do its thing all over again. So any questions on 7.2? All right, here's 7.3 from the current slide. Still doing applications of integration. In 7.3, we're going to talk about also getting volumes, but this time we're going to use a different method. Before we used discs or washers, now we're using shells. Okay? Now, there is a reason for having two different kinds. It's not just for duplicating, though some problems could be worked either way, but you do the one that comes out the easiest integration, the easiest setup, whatever that happens to be. So our objectives here are to find the volume of a solid of revolution using a different method, not a disk method. This will be a shell method. We'll compare the uses of the disk method with the shell method and see if we can come up with any generalizations that help you see which one would be better or worse to do. So here's the shell method. An alternative method for finding the volume of solid of revolution is the shell method, because it uses cylindrical shells. A comparison of the advantages of the shell in this method will be given later in this section. So let's do this. Let's take I think it's pretty close to the same thing we had before, somewhat similar, that we have a little wedge here, a little rectangle that we're going to revolve around the axis of revolution. Okay? W is the width of the rectangle that I think you'll see will later become maybe a dy, perhaps. That looks like that would be a good case for that. And H is going to be the length of that shell, the height. If it stood up this way, it would be the height. And P is the distance between the axis of revolution and the center of the rectangle. That is your P here. We were calling the radius. Okay? Now, because we actually do have a W here, not a dy perhaps, it has a finite length, so you're going from P, from this of P minus W over 2 to this is P plus W over 2. Don't let that work you too badly, because we're going to go that be infinitesimal, so it's not really going to matter. Okay? And I guess P is the center of that rectangle, is what we understand. P is the distance between the axis of revolution and the center of the rectangle. That's what I have to do, plus and minus W over 2. Okay. When that rectangle is revolved around the axis of revolution, it forms a cylindrical shell or a tube of thickness W. And that W can be very small. We could get down to a dy, say. To find the volume of that shell, let's not have a dy yet, consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell. The radius of the smaller cylinder corresponds to the inner radius of the shell. Because P is the average between those two radii, you know that the outer radius is P plus W over 2, and that's what we were seeing before in the picture, and the inner radius is P minus W over 2. Okay, we obviously approach that, and dealt with that. So the volume of the shell is the volume of the bigger cylinder minus the volume of the hole. A lot like we did in the washer method, the outer minus the inner. Okay? Except now, what's the volume of that cylinder? It's not before with the washer method, it was the radius that you were increasing or decreasing. And, it sort of is here too, but it's a P plus W over 2 squared versus a P minus W over 2 squared. The height is the same. Now, they jump from here to there with nothing more than just saying, this is that. What you have to do is actually do these squares. Okay, obviously you see the pi's are going to come out of both of those. And the h's are going to come out of both of those. So that leaves a 2p and a w. They haven't accounted for it here. So let's deal with that and see how they got 2p and w there. Okay? Let's square this. And this is pretty straightforward, I hope. This is p squared plus twice the cross product, right? Square the first, twice the product of the two, square the last. Remember, that's how we square a binomial. Everybody remember that, right? So twice P times W over 2, well, the 2 is going to cancel the 2. That would be just PW. Okay? Plus, and you square the last one, that's W squared over 4. Okay? Now, we've already taken care of, pulled out the pi and pulled out the h. Okay? And this is, why can't I find no color, right? Okay. Okay. So that's this first square. Like I said, we already pulled out the pi and the h, factored those out, so we're just doing this thing minus that thing squared. That thing squared is going to be fairly similar. Minus, this will be a p squared, minus pw. Because twice pw over 2, the 2's cancel out, and then plus w squared over 4, right? And if you subtract these things, the p squareds go out. P squared minus p squared is 0. And the w squared over 4, this is a plus, there's a minus. They go out, and that leaves you with 2pw, because minus and minus is plus, pw plus bw is 2pw. And that's where you get the 2pw. So sure enough, they did it right. Now, so the 2 pi's come out, and that leaves you the p, which is the average radius, remember, of that circle of little square that you're revolving around the x-axis. Okay? And w, h times w is the height times the thickness, which basically is the area of that little rectangle. Okay? So let's go back and see. 2 pi times the average thickness, E, times h times w, which is the area. So in other words, you're taking that area, revolving it around here, and by the way, what's 2 pi times this p here? 2 pi r. Help me somebody.
What would be the point of using this method compared to the washer method?
Okay, we'll get to that. Believe me, we will. Some functions, if the washer method has you going from one side of the function to another side, that's really awkward and messy to do. Especially then if you have 2 different functions on either side, that gets even worse. So there are times when the shell will work out really, really nicely versus the washer or the disc won't. The washer and disc work most of the time very well. There are certain sections they really stink. Now, what my inclination to have done with this, they've turned around and done it. It made it so confusing to get there. Okay? What I would say to do, here's the shell, right? You got the dimensions on it. I say take your scissors and cut right down the middle of that shell. Okay? Nice straight line. Okay? Let's take that shell and flatten it out. Okay? Now the thickness of there is W, right? And the length of that is H. Well, the width of that is H. And the length of it is, when you flatten that out, is circumference of this thing. What's the circumference of that? 2 pi. 2 pi times the radius. So that's where you got this. Okay. 2 pi times the radius, that's the circumference of that shell, times the height of the shell times the thickness of the shell. You flattened it out and made a rectangle. The rectangular solid. 2 pi r is the length of that, h is the width of that, and w is the thickness of that. So to me, that's a lot easier than doing this difference. Now, I was afraid if I did it my way, it would come out a little different. It comes out exactly the same. Okay? So you can use that formula to find the volume of a solid of revolution. So let's see if we can do it. Here we have a triangular shape. Okay? And this is, if this is your y-axis, you don't state it knows your x-axis. You really don't need to know the x-axis too much, because that's the y. The reason I say it's the y is your dy. That's going to be the thickness. Okay? You're going to take this triangle and rotate it about, I think it's the y-axis, I mean the x-axis here. And that's going to give you a, not a very creative looking, but a Christmas tree stand. Okay? The cylinder in the middle, that's the whole part here, and then this part is the, you could also call it a frustrum of the cone of the cylinder, really. Okay, or something like that. There's all sorts of things you can call it. You can call it Fred if you want to. Okay. So, what would be the volume of that if you're revolving that around? So let's do this little horizontal rectangle here. Its length is the h of y. Now, you're going to have to come up with that as a function of y because you've got a dy here. The h of y times dy is the area of that. The radius of that you're going around here, so you're going to have 2 pi to p. That's going to be p as a function of y. It just looks like y to me, doesn't it? If this is the x-axis, that is the y-axis. This is just y value. Okay? So why they said p of y, that's fine. That's the radius. So 2 pi times y times this h of y, but you're going to have to get it in terms of y times dy. Okay. And what does that mean? That h of y. Somewhat similar to what we did before. Well, they just leave it there because they didn't give you any measurements from it. I thought they were going to give you some values in here. They don't. So this is what you got. 2 pi times the radius, which is in this case going to just be y, times your h of y, that's your length, times your dy, that's your width. There is the thing. That's your delta v. Okay? So it's pretty straightforward and pretty simple, not too bad. Now consider that blah, blah, blah. Okay, I think we've got that done. Okay? And that's what we're going to integrate to get the total volume. By the way, the 2 pi will always come out front, and then any other constants you can too. You can approximate the volume of a solid by n such thicknesses of shell, delta y. Yeah, we got all that coming. The h of y, we're going to have to calculate. The average radius is just going to be your y. Okay? Please, when are they going to get around to telling you that? But it could be if you're doing for some other thing, it's still going to be a p of y. Okay? So this is what you get, and when you take the limit as your deltas are getting smaller and smaller and smaller, meaning the end's going to infinity, the volume of the solid would be 2 pi times the integral from c to d. Those, by the way, are your limits on the y from c to d. That's the limit on y because that's what you do your delta y over. Times your h of y, which is the length of any strip there, times dy, which is the thickness. So 2 pi radius height times width. That's your volume. Just like you, I hope you would expect if you cut the shell in two, and you've done it 2 pi radius times the height times the thickness. Okay? And so here we have it. To find the volume of a solid revolution with the shell method, use one of the formulas below. If you have a horizontal axis of rotation, then the volume is 2 pi. That's a constant. Always comes up in front. If it's about a horizontal axis of revolution, then the P of y is going to be the radius. You see, this doesn't have to be the x-axis. This could be x equals 0, could be right here or anywhere below, okay? And your axis of revolution, this is just going to be some y value, either 0 if the x-axis is here, or greater if it's here, less is the other. So less smaller axis is here. Smaller r if the axis is here, because it's going to be y minus whatever value that is. So that's just your P of y, whatever that happens to be. The h of y is going to be h of y. That's the thing we haven't figured out how to define yet. And then the dy here. So this is leaving it pretty simple. But if you have a vertical axis of rotation, then your cylindrical shell is going to be some h of x, okay? The 2 pi times the radius, whatever that is. You have to calculate, figure that. It's usually pretty easy, just a difference usually. Times the h of x, which you're going to have to calculate. That's the hard part, times the dx. So that's what works if it's a horizontal axis. A vertical axis. Horizontal axis is going to result in dy shell, vertical axis is a dx shell. Whereas, for the disk method, if you're revolving around this, you would have a dx. If you're revolving around the horizontal axis, you have your dx. In a vertical method, you have your dy. So that's one big thing. So if it's easier to deal with the function of the variable perpendicular to the axis of rotation as opposed to parallel to it. So that's going to be our determining factor. So let's do example 1 where we actually have a problem, okay, not just a figure. And this, I think, is on page 466, okay? Find the volume of the solid formed by revolving the region bounded by y is equal to x minus x cubed and the y-axis and the x-axis between 0 and 1, okay, on x, about the y-axis. So the first thing we got to do is draw a figure, okay? So let me draw I'll keep it generic to begin with. Y is equal to x minus x cubed. Give me some values for that, especially between 0 and 1. So here's 0, and let's just say this is x equal 1. And we'll put y up here of 1, okay? And we're going to use the y-axis to revolve around. So what does this function look like? X equals 0, what is it? X equals 0, what's that? Pretty easy to do. 0. Okay, good. And let's go to the other endpoint where x equals 1. What is its value? 0. Okay. Wow. Okay. Let's say 0.5. What would that one be? 0.5 minus 0.5 cubed. Anybody know? Is that right? Because 5 squared is 25 and 5 cubed is 125. But you got decimals in there. So this is going to be something like 0.375, isn't it? There's .375 is going to be somewhere here. So that would be about here. Let's do a 0.1. That's going to be easier. 0.1 minus 0.001, right? That would be 0.999. Right? Wait a minute. 0.099. So 1/10, that would be a half. Tenth will be here is 0.019. So it's going to be here. So I think, well, let's take something close to the end there, like 0.9. Ooh, 0.9 is a big number, but 0.9 cubed is going to be small. Let me just cheat and look at the book. Example 1, yeah. It's going to go up here slowly and come down a bit more abruptly. Okay, that's not a really good. Going to revolve that around the y-axis. Okay, so you're going to have this going around here. Okay, so that's going to be a, I don't know what that would be. It would be going like this over here and that all the way around. I can't think how to, any practical thing that would look like. That's probably not quite legitimate. And that's going all the way around. Part of it almost looks like a torus, but it isn't because it's connected in the middle. Okay? But that's what you've got. Now, if you were trying to do a washer method, which is the question, this is around the y-axis, you would do your dy's, and it would be this minus this. And those are kind of, you would have to get this in terms of y, and to get this function in terms of y, oh no. You know, that's really ugly. Okay. So this thing, doing the dx is going to be much better. Here's your dx. Okay, and what's the height of that? That's your y, isn't it? Because you're going from the x-axis, okay? Bounded by the x-axis between 0 and 1, and those are your endpoints. So the height here is going to be your y. Your width is going to be the dx. The radius is going to be your x, okay? Which is not too good because now you, oh boy, that does present a problem. You still have to find no, your dx, yeah, that's just x. Your y, you know what y is. It is this thing right here. Okay, I'm sorry. This is x minus x cubed. Okay, your dx, and this is just going to be your radius is going to be your x. So you got all the pieces you need. Okay, the volume of that shell is going to be the 2 pi r. That's going to be the length of the shell. So that's going to be 2 pi times the integral. And by the way, you're using dx's. They're going from 0 to 1. 0 to 1 of your radius is going to be your x, right? Your height is going to be your y, which is x minus x cubed. And then your thickness is going to be your dx. There you have it, don't you? That just comes out a pretty simple thing. Now, got a little bit to do before you do your integration, but it's not much. V is going to be 2 pi, and what does this give you? Integral from 0 to 1 of, multiply that, what do you get? X squared minus x to the 4th dx. Okay, so v is equal to 2 pi. What's the antiderivative of x squared? X3 cubed over 3 minus x to the 5th over 5, evaluated from 0 to 1. Now, this is a tough one to evaluate, so let's see, dig in and see what we can get. 2 pi times, I'll do the 0 part, you do the 1 part. What do you get when you plug in a 1? It's not that hard. 1/3 minus 1/5. I'll do the 0 part, minus 0 minus 0. Okay, got it. Done. Okay. Now, the rest of it is math. That's not particularly fun either, but it's not too bad. 2 pi. What's the least common denominator? 15. How many 15s is 1/3? 5 15ths minus, how many 15ths is 1/5? 3 15ths. And what's that difference? 2 pi times 2 15ths, which looks a lot like 4 pi over 15. Okay? Now, we can see what they got. Oh my goodness, look at that. They got 4 pi over 15. And just to get an idea of what that is, pi is a little more than 3, right? So that would be a little bit more than 12/15, which is a little bit more than 3/4, right? So, not a very big area, or volume. Because see, it doesn't even reach up to 1, and you have a hole in the middle of most of it, so there we have. And believe me, you don't want to do this by the disc or wash your mouth at all. Okay. So that's how we did it. Let's see if they do anything any differently. I don't think so, but let's just see if they have some nuances that I didn't get. First, the drawing of the graph. I'm glad they did it. I'll let you it. Okay. Now what we do is your 2 pi times the radius. That's going to give you the length of that flattened rectangle that you have. Okay? So 2 pi to the radius is just x. That's your x value. So 2 pi x times the height of this, which is your y, which is x minus x cubed, times the thickness, which is dx. That's what you get. And that becomes, when you plug all that in, and write it several times that way, okay, that gives you exactly what we got. 2 pi times the integral from 0 to 1 of x times x minus x cubed, radius times height times thickness, and that gives you, oh, I would really like putting the minus x to the 4th in front. I don't know why. That gives you minus x 5th over 5 plus x cubed over 3, which isn't particularly helpful in my book. So 2 pi times negative 1/5 plus 1/3, and that's 2 pi times a positive 2/15, which is 4 pi over 5/15. Okay, that was, excuse me, example 1. They skip example 2, so let's go back and do example 2 on this part. Who wants to guess that maybe this one's a little more complicated than the previous one? They love to skip the complicated. Did I get everybody here when you came in? Did I get you? Yeah, I thought so. Okay, second. Corbett. Yeah. All right. I just happened to notice I didn't think I would know. Anyone else sneak in while I'm looking? Trying to sneak past my security system. Okay. All right. Example 2. Now, it says here, find the volume of the solid formed by revolving the region bounded by the graph of x is equal to e to the minus y squared. Yeah, this isn't any more complicated than the last one, is it? All right. Number 1, what you got is x is a function of y rather than y is a function of x. Okay? So now we're dealing with things sideways here. And x is equal to e to the minus y squared, the volume of the solid formed by revolving the region bounded by that curve and the y-axis between 0 and 1 about the x-axis. So first thing we better do is come up with some sort of, we're going 0 to 1. We'll leave, I'll put the tick marks in there, but I don't know what dimensions we'll be needing there. So you give me a y and I'll calculate the x. Oh, let me write it down. So I should do that first. X is equal to e to the minus y squared. Okay? So since it's y is your independent variable, give me a y. And guess what? They've already told you between, oh no, they didn't tell you how far. But give me a y. Well, we'll figure out how far. The x's are going between, no, the y's are going between 0 and 1. Yeah, I'm doing right. Okay. Y is going between 0 and 1. So give me for 0. What is the x value when y is equal to 0? 1. Okay, so that's where we're starting. Okay. Now give me, let's do the 0. Okay. Plus x going, I'm sorry. Yeah. Y is going from 0 to 1. So let's do y is equal to 1. And what do you get? 1 squared is obviously 1. Okay. And how about e to the minus 1, which is 1 over e? Well, what is e approximately? Anyone know the value of e? Second? 2.7-ish. So let's just round that to 3, okay? Just for the purposes here. So that, let's make that 3. So that would be about 1/3. So when y is equal to 1, x is equal to about 1/3. Something about like that. This is just approximate anyway. Okay? Now, you can do some value in between, or you can just cheat and look and see what they got. And they got something that looks like that, a little bit. Not very much, but a little bit. So that's the volume that you got. And you're revolving this around the x-axis, right? About the x-axis, right? Okay? So basically, you're going to have something that goes like okay, that revolves around here. Now that's not a very good picture. Okay, something like that. Okay? Now, anyone want to go for the x's here? Not me. Okay? So let's try your dy's here. Okay? So that's going to be a shell. A shell going around there. Okay? Let's see what we got. And I said that's about 1/3, but remember what it really is? This is 1 over e. Right? That's that value. And this is 1. That's on x. We really don't care about the x. We're doing dy's. So here's your dy. Okay? Now the volume is equal to 2 pi times that radius. Oh yeah, and the y's are going from 0 to 1. Right? Yeah. Y is going 0 to 1. I didn't write the whole problem. I probably should have. Y is going 0 to 1. Your radius. Here's your radius. Guess what that is? Not 1. This is your y-axis. This is your x-axis. Your radius is y. Why not? Okay? Now, what's the length of this? X minus 1 over e. Right? That's the length of it. So it would be x minus 1 over e. But what is x? X is e to the minus y squared minus, what was that? Minus 1 over e, wasn't it? Okay. So there's your length of that. And of course your thickness is dy. Now, I think that's it. I think that is your integral. Let me just look and make sure. Y times, okay. Let me hold on just a minute. No, I'm sorry. This is all part of the solid. Okay? That's going around. I don't know if you can justify that. I may have misread something here. Bounded by the graph of that and the y-axis. I don't see anything here that says cut off that piece. It says find the volume of the solid formed by revolving that region. It only goes to there, around, bounded by that graph, and the y-axis. Okay, bounded by the graph of that and the y-axis. So yeah. That statement that it's bounded by the y-axis pulls it over there. Okay. Sorry about that. I had to be convinced that was intended. And it is. I hadn't seen and the y-axis there, between there. So yeah, you are including this here. Bounded by plus and minus, or 0 to plus 1, the y-axis, and this curve. So that's what gives it to you. That's why this isn't involved. So then you don't have this minus 1 over e. Sorry about that. That's not included. Okay. So there's what you got. And that's all you've got here. Okay? Now, shame on them. Okay? They are actually having you do a substitution. Oh, but y'all did that, didn't you? That's right. I was thinking, okay. Sorry. You've already done the substitution method, right? In some earlier life, okay? So you know how to do this. You folks from my class, we didn't get to it. Sorry about this. So I'll show you how to do this real quickly, okay? Here we have, it's not a composite function, it's a product of two functions. Okay? Well, we don't have a undoing a product rule as an integral. Okay? So we're going to have to deal with an integral somehow, a thing with that. And here's what we're going to do. We're going to treat this as if it's a chain rule problem, because that's really what it turns out to be. We don't know how to undo a product, so let's try something else. This is a composite function of e to some other function, Okay? Now, if this thing outside here was any way related to the chain rule derivative of that, you might have something you can work with. So let's say, let's make it so, or at least assume it might be. So let's change this to because the more complicated function here is obviously the e function, right? So let's let everybody's favorite is u equal minus y squared. Okay? You all right with that? Okay. Then we're going to take a derivative, or a differential. du is equal to what? What's the derivative of minus 2y, of minus y squared? Minus 2y dy. We're doing a differential, not a derivative, right? Everybody got that one? Okay. Now, how does this compare to what we have here? This part can be e to the u, and that covers this part. The y dy looks pretty close to that, but not quite the same. So that's going to be, to make this look like y dy, see, here's the e to the y, e to the u. To make this, let's do divide both sides by a negative 2. Okay? And that then gives you negative du over 2 is equal to y dy. By that? Okay? So this is going to produce e to the u, and this is going to be your du. So let's plug these in here, and that'll be a 2 pi times the integral. Now I've changed my variable from y to u. We won't worry about that yet. Oh, let me see. I do want to worry about something. I have to worry about something. Okay? Here's what we have. We've got a negative 1/2 out front, so that's going to change that 2 pi to a negative pi, because you're dividing by 2 and multiplying by negative. Okay? Now this is going from, we haven't decided what it's going from yet, but your argument here, the y dy is that negative, so that's going to be your du, because we already pulled out the negative 1/2. Okay? And the u part, this is e to the u. Okay. Do you see that that gives you that? Okay? Do the inner function of your e to the something or other, let that be your u. Let u equal negative 2y. Negative y squared. Okay? Then take a derivative. Du is negative 2y dy. Okay? Divide by negative 2 and you get negative 1/2 du. I should have written it that way. Is equal to y dy. So here's your y dy. That's negative 1/2 du. Well, the negative 1/2 wipes out the 2 here and makes it a negative. So here we have the integral of e to the u du. But this is the dy going from 0 to 1. We need our u to figure out what u is going from. Okay? Now, when y is 0, what is u? Any guesses? When y is 0, what is u? Because y is 0 here, what would u be down here? 0. Okay, I could do that one. Okay. When y is 1, what is u? Y is 1, what is u? Negative 1. Okay? Well, I don't like going from the 0 to negative 1. I like to go from, say, negative 1 to 0. But if you change your limits on the integral, what do? Negate, right? If you're doing the area from here to there, that's a negative area. If you do it from here to here, that's a positive area. So, or vice versa. So you're negating what you have. So if you flip these over, this will negate this. Well, there goes your minus sign. Okay? So you have pi times the integral from -1 to 0 of e to the u du. Okay? That's going to be pi. And what's the antiderivative of e to the u? Now, y'all didn't do this either, but does anyone know what that is? It's my favorite of all time. It's e to the u, because what's the derivative of e to the u? E to the u. So the antiderivative of e to the u is e to the u. So we've run that to death, haven't we? E to the u, and then we're going to evaluate that from u equal -1 to u equals 0. Okay? And that's going to be pi times, and what's e to the 0? Say again? 1. Okay, anything to the 0th power is 1 minus e to the -1. Okay? Now that's a legitimate answer. It may not be the one they give. Yes, it is. Pi times 1 minus, well, they write this as pi times 1 minus 1 over e, which is e to the -1. Okay? Or you could write that as pi times e minus 1 over e. Whichever way you want to write it. And if you plug it into the calculator, you'll get approximately 2. About 1.986. Very close to 2. Okay? So that's how they did example 2. Had some new stuff, but some, for those who have already had substitution method, is nothing new. Now, the exploration here, for those who prefer the disk method, here's how you would have to do it. You would have to change the x equal e to the -y squared to be y is equal to either 1 when you're less than 1 over e, which is what I was showing there, and negative, the square root of the negative log x from 1 over e to 1. Okay? I don't want to go there. Okay? If you do, knock yourself out. Okay? Now, that was example 2. Now we're going to compare them, and this hopefully will answer your question. Why do you even mess with the shell method? This method seems to work very nicely because we chose problems that it works very nicely with. And then for those that didn't, we choose those for this. So here's how they can be distinguished. For the disk method, the representative rectangle is always perpendicular to the axis of revolution. Because if you're revolving around the x-axis, then you're taking your the rectangle they're saying this sort of string. If this is the axis of rotation, the y-axis, then the representative rectangle is going to be perpendicular to that, which means a dy. I like to think in terms of axis of rotation and that, and that's why we'll never say the rectangle. I really don't think in terms of rectangles. I think of your dy's, okay? If you're revolving around y, take your dy, and that's going to give you your disk, okay? Which makes the rectangle perpendicular to that. Okay, fine. When you're doing the shell method around that, you're revolving around the x-axis, then you're doing the dx then, okay? No, I'm sorry. When you're doing the revolving around the x-axis, a you're taking a dx. Okay? So your rectangle is perpendicular to that. But when you're doing the shell method, you're revolving the shell, so your d around the y-axis. So you're going to take your dx's because that makes the shell around the y-axis. Okay? So that makes it parallel. I don't think in terms of parallel, I think around the y-axis you take a dx. Around the x-axis you take a dy. Which of course makes a rectangle perpendicular. Okay? Now, the other thing is, if you have the washer, not this, but washer, then you have to do r squared minus, big R squared minus little r squared. If it's going around this axis, and they show this to be the x-axis, then you are leaving a hole in this part. So you're going from little r here to capital R there. The other end of the shell. Whereas a disc, your radius is just on the, things are like this, the radius is just your distance from the dx to whatever your axis of revolution is. Here, if it's a y, that's just the x value. So if you're taking dx, it's a rectangle. If you're over here, it would be x minus a minus something. If you're in here, x minus whatever value that is. So whatever that ratio, that difference is, it's the y-axis is just x. Whereas, I think we've hit all the possibilities there. Here, your radius would be your y, or if you're going from some other axis rotation, y minus plus whatever the value would be. So let's do example 3, which I think is going to, and by the way, example 3 is also at LarsonCalculus.com. Okay. Find the volume of solid form by revolving the region bounded by the graphs of y is equal to x squared plus 1, y is equal to 0, x equals 0, and x equal 1 about the y-axis. So, you're going from y is equal to 0 up, okay? X squared plus 1, if there's your 1, there's a 1, there's a 1. There's a 2, 3, 4, 5. Oh, we don't need that many. We're just going x equals 0 to 1. That's all we're doing. Sorry. Okay? So we don't need this over here necessarily. So this is going from when x equals 0, this will be 1. Y is equal to 1. When x is equal to 1, y is equal to 2. Okay? So basically it's the part of a parabola, because that's a parabolic shape there. Y is equal to 0 is down here. X equals 0 is here, of course, and x equal 1 is here, of course. Okay? So this is the part you're dealing with. This part right in here, revolving that around the y-axis. So that'll go to something over here. This will be revolved around there. Okay?
What is the point on the y-axis?
What's that?
What is the point on the y-axis?
Okay. This is 1, 2. Is that what you mean? Okay. Yeah. I set it here. I need to do that for x2. 0, 1, 2. And we don't ever get out the 2. So this goes to minus 1. This goes 0 down here. And 1 right here. Okay. Now, let's take a look and see what we figured you'll have to and revolve around the y-axis. Okay. Do you think it's better doing this here In other words, dy's, and you're going from here to here. That won't be hard for this part of the disk, but for this part, you've got washers, and the washer's going from one to this, but you'll need that in terms of y, so you have to, then the x squared is equal to y minus 1, so x is equal to the square root of y minus 1. You want to integrate that? I don't either. So I think here, shell method might be better. Taking a dx, your radius is just your x value. Your height is your y value, which is x squared minus 1, already determined that, and your thickness is dx. So I think that's the way I'd like to go. Would you? Okay. So let's take our dx's here. Okay. And our radius here is x. Okay. So our integral here is 2 pi times the radius, so the 2 pi on the outside, times the radius of x, okay, times the height here. There's the height, x squared plus 1, and then the thickness is dx, okay? And what is your, since you're doing a dx, your limit of x is going from 0 to 1. Yeah, there it is. They gave you that to begin with, 0 to 1. Okay? One little thing you got to do before you proceed any further is what? Multiply through there. What does that give you? X cubed, second, plus x dx. Now you do your antiderivative. That's 2 pi times x to the 4th over 4 plus x squared over 2, evaluated from 0 to 1. That would be 2 pi. 1/4 plus 1/2. Okay, minus 0. I did that part. And this would be 2 pi times, that's 3/4, isn't it? And that would be 3 pi over 2. All right. Goodness gracious. 3 pi over 2. Good deal. All right. Now, sorry I didn't stop sooner, but do y'all need a break? I know one person took one, but you need a break? Okay. We've been at it for basically, what, an hour and a half. We got an hour and 10 minutes left, so it's a good break time. So let's do this. Try to keep it short. All right, so that was the end of example 3. They do have a little blurb at the bottom of the page, 468. It says, to learn more about the disk and shell methods, see the article, The Disk and Shell Method, by Charles Cable in the American Mathematical Monthly. To view this article, go to matharticles.com. So that's a nice reference they give you there. And if you wanted to do, because this is something outside the book, you could use that as one of your sources, if not the only source, of a paper. All right, so we did this. I should have really shown you what they did first. I didn't think about it. They've already done this. So let's review example 3. The washer method requires 2 integrals to determine the volume of the solid. One is a real simple integral here. In fact, you can just do the area of the circle times the height. That would be pretty easy to do. Pi r squared times 1. And that would give it to you. So that would just be pi. Okay? Then the second part, you have to go from here to there, but you have to get the radius in terms of the outer radius is 1, the inner radius is the square root of y minus 1, which we talked about before. And you have to, and that wouldn't be super bad either, because you're going to square both of those. And you're going from 1 to 2 on that, and y is equal to 1 to 2 with the dy. So it's not an impossible or terrible integration to do. It's just you have two of them to do. You have to change the variable from y as a function of x to x as a function of y. It's doable, and it's okay. It's not impossible, okay? But it's a little more involved. So that's certainly one way to do it, and you can certainly do that. And here they show you how to do that. Make it hard because it's really easier to do that first part to just be pi, but that's what they get. The second part is pi times 1 squared minus square root of y minus 1 squared, which of course is going to be square root of y minus 1 squared would be y minus 1. It would be 1 minus y minus 1, so that would be 2 minus y. Okay? So that the integral of 1 dy, okay, minus the integral from 1 to 2 of 2 minus y. And the first one, boy, they really string this thing out. That would be, yeah, that. And, you know, really easy integrations on both parts. And that would give you a little bit more math to have to fiddle with. But when you do all that, you get 3/2 pi. So you do get the same answer, and it's not that terrible. But if you did the shell method, like we did, that would just be the okay. Okay, sorry, I was just checking out. I think I was remembering the previous problem. Yeah, I'm sorry. Okay, I was forgetting that we had already done this one. Okay, here's the shell method. Do we have it? Yeah. The shell method is now 2 pi times the radius, which is x, times the width times the height. The height is your f of x, which is, they don't show it here, x squared plus 1 times dx. Pretty easy, single integration to do. Okay, so it's v is equal to 2 pi times the integral from a to b, which is 0 to 1, of x times x squared plus 1 times dx. Plugging that all in. That's a pretty simple integration to do. They left off a step there, x cubed plus x. Then you integrate that, and you get that, which you get that, which you get that. Shorter, simpler, integration's easier, substitution's easier, everything's easier, okay? So that's your choice. In this case, I would go with the shell method. Came out much easier. Whoa! That was example 3. They skipped example 4 and 5. So let's go back and us do 4 and 5. All right. 4 first. A pontoon is to be made in the shape shown in this figure. And they want me to draw this, don't they? Boo hiss. Okay? And then they tell you how it's designed by rotating the graph of y is equal to 1 minus x squared, 1 minus x squared over 16, when that is evaluated between minus 4, starting to do it in interval notation, but they do it in, yuck, I went to get my eraser and then did away with my eraser. That's not doing too well. By the way, just to explain why I'm kind of flaky today and scattered, my wife and I were helping one of our local candidates for several months now, several weeks, I'll put it that way. Well, actually, it goes a little longer than that, but pretty intensively the last few weeks. And so we were invited to the watch party for the results last night, and we were hoping to be out of there fairly soon. Well, unfortunately, his was just about the only race that, I mean, he led by a large margin all night long, but there were 3 candidates, and he kept right, usually above 50%, and the other 2 were splitting the other split, and then right at the end, they were at 81% for like an hour, never updating. And we thought, let's get a little bit more, we think he got it. When they finally went to 81% of the ballots, he dropped to 49%, and this woman swapped with the guy who was below her, so they were neck and neck, but way back there, and so we kept going, surely we're going to know, and actually someone got word someone was projecting he was going to come out a winner, so we were just on the edge waiting to see, finally left when it was still 49%, and by the time we got home, got everything situated and stuff, we still didn't know the answer. This morning we woke up and he was going to run off. So it was so disappointing. But it was that close, but we didn't intend to be there that late. But that's my problem, not yours. Okay, so here is your situation. -4 less than or equal to x less than or equal to +4. Now, not everybody has books, right? So let me go on and draw this one. Okay, I'm not going to need much, okay? On the x-axis, this is going from 1, 2, 3, 4. -1, -2, -3, -4. So let's pick a few values to evaluate that. How about x equals 0? That's always an easy one. That goes up to 1. And we'll write a -1 down here, so we're only going to do the top half. Okay? Okay? When x is equal to 4, I think you see that's going to be 0 and 0. Okay? And then this acts a lot like it is a parabola, so just give it your best shot of drawing a parabola there. And then you're going to revolve this around the y-axis, right? And that forms your pontoon, so it does something like that, okay? A little more pointed at the ends than I have it, but you get the general. This end looks better than that one. That one looks too rounded, okay? Doesn't matter about the picture, the math will take care of it. Calculus will fix everything, right? We're going to revolve that around the x-axis where x and y are measured in feet. Find the volume of the pontoon. Okay? Now, you tell me which method you want to use. Shall. Okay? What would be your d's then? dx's or dy's? Dy's. Okay, he's wanting to do a dy. okay, and your y is going from 0 to 1, okay. And your radius will be y. That's not going to be too bad. But your length there is going to be x, so you have to get that expression in terms of x in terms of y rather than y's in terms of x's. Not terrible, okay? Not terrible. So that certainly could be done. Why did you not like the...
Would it be easier to do the washer with the dy's? Or no, the dx?
With the dx. I think so, because now you don't have to change it, and it's not really a washer, it's a disc, because there's no hole in it, okay? I hope you don't have a hole in your pontoon, or you're not going to keep your boat up, okay? So let's try that, okay? Let's do a dx here, okay? So this is going to be your dx, and okay, remind me how to do that though. How do we do that? You need the volume of this little disc, right? The volume of the disc is the surface area of the disc is a circle, okay, of radius y. So there's your radius right there, okay? And you're going to, the thickness is dx, and you've got enough to go from, okay, now here's how I'm going to cheat a little bit, because I'm really lazy. This half of the pontoon looks just like this half, right? Doesn't look like it in my picture, but in their picture it does, right? So let's just go 0 to 4 and double, right? Because you're doing dx's. So let's recap that then. We're going the integral from twice the integral from 0 to 4, okay? And the area of this disk, you're going to sum up all these 0 to 4. The area of the disk is the radius of that. Well, the radius of that is your y value, which is this. So it's pi, area of a circle is pi r squared. So here's your r, 1 minus x squared over 16 times dx, right? That's it. You're summing all those disks. The 2 is out there because you're going from, we're going 0 to 4, we've got to double that to go minus 4 to 4. But everything else there is the same. It's a symmetric function. Oh, pi r squared. I forgot to square my thing. I said it, but I didn't write it. So first we have to do 2 pi times the integral from 0 to 4. Okay? We got to square that thing. So what is that thing squared? Help me. 1, good. Minus twice the product of these two. That would be twice 1 times x squared over 16, right? And 2 will go into 16 8 times. Okay? And then what's the last part? Plus this thing squared, which would be x to the 4th over, and what is 16 squared? 256, is that it? That's what I think it is. Someone check me out. 256, okay? And that will be times your dx. Okay, yeah, the numbers are getting sort of big and ugly. But 2 pi, I think we can still do the integration. What's the antiderivative of 1? Or 1 dx. Antiderivative of dx. x, okay, minus antiderivative of x squared over 8. X cubed over 24 plus antiderivative of x fourth over 256. X fifth over, let me just put 5 times 256. I don't want to do that one in my head. Okay? All right, the fractions stink. Maybe the cylindrical method would have been better, but I have a feeling you're going to have messy numbers no matter how you do it. So, what do we do from here? And that's evaluated from 0 to 4, because we already doubled it to take care of the other half. So, these are going to be some pretty ugly numbers. So, let's start with the 2 pi times, I can do the first one, 4, okay, minus, now what we have here is 4 to the third, which by the way is 64, but let's do it a little smarter than that, okay. Remember this was 6 times 4, and this will be 4 to the thirds, so cancel that. That's 4 squared over 6. Well, let's see. That would be 16 over 6. We'll come back and simplify that in a minute, okay? Plus, well, again, let's be a little bit smarter about this. This is 4 to the 5th power divided by 5 times, and 256. Remember, that was 16 squared. So that was 4 to the 4th power, right? Isn't that what 16 squared is? Okay. So 4 to the 4th will go into 4 to the 5th 4 times. So that last is going to be a 4/5. That keeps the numbers a little smaller and more reasonable. So this is going to be 2 pi times 4 minus 8 thirds plus 4/5. If I'm doing it right, I hope I have. Least common denominator is going to be 15. So that's going to be 2 pi times, well, 4 and 15ths would be 60 15ths, right? Minus 40 15ths, right? Plus 12 15ths. Okay? Now, let me come up somewhere else and do that. 2 pi times 60 minus 40 is 20, plus 12 is 32 15ths, which I think that comes out to be 64/15 pi. I don't think there's any way, if that's the right answer, no matter which method you use, is going to stink. Oh, and by the way, that does come out 64/15 pi. And again, if you approximate pi to be about 3, that would be 64/5. 5 will go into 64 something more than 12 times. So when they say the answer is about 13.4, that's reasonable. And by the way, since this was given in feet, this is cubic feet. Okay? Cubic feet. By the way, 13 cubic feet is not huge, but it's reasonably big. Okay. Now, to do the shell method, you would have to solve x in terms of y, okay, and that would give you a square root. You don't have the squaring of it then, so they say then you'd have to use a u substitution like we did before. Have a feeling that would be a little more difficult. But it says sometimes solving for x is very difficult or sometimes even impossible. In such cases, try to do the disk. If changing the thing is going to make it miserable. Okay? Any questions on that before I erase it? Okay. Let's do example 5. They do the easy ones and don't show the harder ones. Find the volume of the solid formed by revolving the region bounded by the graphs of, I had something on my page there, y is equal to x cubed plus x plus 1, y is equal to 1, and x is equal to 1. About the line, ooh, goodness, oh yeah, that's okay. About the line x equal 2. Okay? Shown in the figure. Thank you very much for giving me the figure, but you don't show it on the slide set, so I have to still draw it anyway. Okay? So let's do this. It said about the line x equal 2. So here's your axis, and x equal y cubed plus y plus 1. There's 1, 2, 3, 4. Okay. 1, 2. Okay. So when x equals 0, y is equal to 1. When x equals 1, y is equal to 3. Right? Okay. I'm just going to take their word for it. It goes something like that. Okay? So there's that function. Y is equal to 1 is this line right here. X equal 1 is that line right there. So it's that kind of a triangular looking region that we're dealing with. Now, revolved around the axis x equal 2. That's where we're going with it. Okay? Not the x-axis. Okay? So this is either going to be a washer or a shell. Which would you like to use? So around the x-axis, I mean the line x equal 2, that's that line here. So the other half of this will be over here. Okay, that would be what you got here. Now, the question is, do you do dx's, which are going to be shells, or dy's, which are going to be your discs, or washers, actually. Sure, about x equal 2. Yeah, okay, sorry. I thought when I read this, it said this method necessary. I said, please don't make me do that, okay? No, the shell method is necessary. And the reason why is because with the shell method, we're going to have dx's, right? Okay, and this is going around there. And you already got y in terms of x. If you're doing the disk method and you do dy's, or the washer method, dy's, then you have to get this in terms of x. I mean, this in terms of y. X is a function of y. Do you think you can do that? You win the Fields Medal if you can, okay? They don't have Nobel Prizes for mathematics, but the Fields Medal is the thing. You can get that as a function of y. Yeah, Do it. You win big time, okay? You're celebrated, okay? You probably don't need, no, never mind. Not going to happen, okay? So we've got to use the shell method here. Stick with our dx's because this is in terms of x. And the height here is just simply the function minus 1, okay? This function minus 1, which actually would be a pretty easy thing to do. Your dx, that's going to be fine. And your limit's going to be I want to say 0 to 1. Yeah, that'll be okay too, I think. But it's going around that way.
Could you do it from 1 to 2? All right.
Okay. Well, there's nothing in here. But you see, your radius, though, that's the part I left out. The radius here is not x. The radius is 2 minus x. That's the new part, 2 minus x. Okay? So let's get it all down. The shell method would be the integral, and you're doing dx, so that's going to be, let's write it down as 0 to 1. Okay? Hopefully that'll be okay. You got the 2 pi to give you the circumference of your radius, and your radius is 2 minus x. Here is your radius. Here. This is what's being revolved around. Okay? 2 minus x, because this is x right here. Okay? 2 minus x. The height of this is your function here, x cubed plus x plus 1, and then your thickness is dx. Okay. Okay. Let's go for it then. Of course, the hard part of this is you got to multiply two polynomials. It's not impossible, but it is messy. Okay? So let's sock it to it. What would that be? 2 pi times the integral from 0 to 1 of 2x cubed, right? That's your x cubed term. Oh wait, well, going to have more. You have a plus 2x. Okay. You have a plus 2. Then you have a minus x to the 4th, right? Minus x squared. That's this one. And then a minus 1. I think no, minus x. I knew that didn't seem right. Okay. Now, notice you do have two like terms there, but that's all. And then you have a dx. Okay? Unless I did something stupid there, which I may have. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I think I got them all right. Yeah, I believe I'm okay. So let's combine those. That's 2 pi, integral from 0 to 1. I don't mind starting with the 2x cubed. Let's do the minus x to the 4th. This is not in great order. Minus x squared. And then we have plus x, right? dx. And again, this seems a little stupid, but I think it's all right. 2 pi. Did I miss one? Yeah, I left off a term, didn't I? Oh, plus 2, plus 2. I knew I couldn't go from 6 to 4 and only combine 2. So that's a plus 2, right? Yeah. All right. Ooh, I don't need that. Again, the old gray cells ain't working too well today. All right. Antiderivative of 2x cubed. Help me, help me. And say that again. 2x fourth over 2, and 2 over 4 would be x fourth over 2, right? By that? Okay. Next. A little louder. X to the 5th over 5, is that what you said? Say yes. Okay, good. Minus. Okay, x cubed over 3 plus that's an x up there. So what is that?
X squared.
X squared over 2 plus 2x. And that's evaluated from 0 to 1. So it's not going to be too bad because of that nice limit there. 2 pi times, messy fractions, but the rest is not too bad. 1 makes it real easy. 1/2 minus 1/5 minus 1/3 plus 1/2 plus 2. Right? I'll do the 0 part. Done. All right. So 1/2 plus 1/2 will be 1, and 1 and 2 is 3. So you got a positive 3 and a minus 3/15 and 5/15. That's minus 8/15. So that'll be 45/15. That's your 3 part. Get out of there. This thing drives me nuts. Okay, I'm going to have to close this down. So y'all remind me where we are. 45/15 minus, and what did I say it was? 3 and 5 is 8/15. Okay, because I can't do a thing here but close it down. Yuck. 45/15 minus 8/15, right? Okay, let's bring it back up. Drives me nuts. Okay. And I got to change my color back. All right. 45/15. And there wasn't there a 2 pi out in front or pi? 2 pi. 2 pi out front. 45/15 minus 8/15. Is that right? My old gray cells aren't too good. 2 pi times, that would be 37/15. Nice round numbers, I like them, okay? And that would be 74 pi over 15. And I don't think that'll cancel any. Oh, yuck. Kind of messed something up here somewhere, didn't I?
Are you allowed to subtract up the positive 1/2 and the other positive 1/2?
Say that again? Yeah, I know I've already erased it. What did you say? Just
If you cross out the 1/2, the
Yeah.
2 1/2s there. Are you allowed to do that?
okay, yeah, but that added to 1, and then 1
Oh,
and
you
2
put
is
1
3.
there.
That's what I did. Whether that was illegal or not a smart move, I'm not sure. Okay? But what I'm sort of fiddling with now is how they went from 1, 2, 3. Okay. I must have missed a term somewhere. Let's go back and do this. I think I had the, oh, okay. No, I did miss a term. I saw it was coming. I know what I did. I don't have it up here anymore. Remember, we were subtracting 1, weren't we? I forgot to subtract 1. And the 1 minus 1 would disappear. I count. In fact, I wound up with a 2. That was supposed to be subtracted and wound up with a 0. So here's what my integral should have been. I can't go back and reproduce it now, or I guess I could, but I don't want to. Your radius was, I'll reproduce a little bit of it. It was 2 pi times 2 minus x. We had that part. And then we had the other part was this is where I messed up. X cubed plus x plus 1. Okay. Now, I don't have the picture anymore, but if you got it in the book, or if you remember, if you wrote it down, you had that. There should have been a minus 1 in there because you were subtracting 1 from that. Remember? It's the curve not to the bottom. That's where I messed up. I thought of it when I was doing it, but I forgot to subtract it off, because you remember the curve was like this, and you're doing from here to here. I'm sorry, this part in here. Well, this is the curve minus 1. This is y is equal to 1. So I forgot the minus 1. That's where I messed up. Okay, and dx, and that's where we got 2 pi, and then this would have been 2x cubed minus 2x, no, plus 2x, and that's all we would have had, right? Yeah. And then the next part would be a minus x. You could just FOIL this. I don't know what I'm doing. Just FOIL it. 2x cubed plus 2x minus x to the 4th minus x squared. There's our integral. Okay? That's our integral dx. And then this will be 2x fourth over x4 over 2 pi plus x squared, right? I hope I'm doing this right. Minus x fifth over 5 minus x cubed over 3. And then when you plug that from 0 to 1, you get 2 pi times 1/2 plus 1 minus 1/5 minus 1/3. Okay. I think so. Yeah. So that would be 3/2 minus, and there was my, wasn't that 8/15 times 2 pi. So this would have been 2 pi times 45, is it? No, 15. Goodness, where's my brain now? 45. 45 minus 16 over 30. Right. Okay. Which would be 2 pi times, what's that, 29? Which would be 29 pi over 15. Yes, that's what we got. Sorry about that. I forgot to subtract off the 1 here, because you're doing the y, the height of this is this function minus 1. Not right. So that's where I messed up. Okay. That finishes 7.3 finally. Okay. Homework exercises here. I would say do either 3 or 5. They draw the pictures for you. You do that. That's both are at calcchat.com. And then do any of the odds 7 through 11. They don't draw the pictures for you. You have to draw your pictures, and that's all are at CalcChat, but 7's at CalcView. Then do again 13 or 15. They've drawn the pictures for you. You figure out how to do those. So you choose they're both at CalcChat. Then do, when you draw the pictures, any of the odds 17 to 21. All are CalcChat, 17's at CalcView. Then do either 23 or 25 or both, and they're at CalcChat, 23's at CalcView. Do 27, it's at CalcChat and CalcView. Do either 29 or 31 or both, they're at CalcChat, not at CalcView. Do either 33 or 35 or both, they're at CalcChat, not at CalcView. 37 and 39, 37 is basically describing something. 39 is actually basically telling why two things are true, okay? Comparing two integrals. So try those. They're a little more, again, esoteric. If you don't want to do them, you don't have to. 41's not a bad one to look at. Either 43 or 45 are good problems. They're both at CalcChat. And then some word problems, any of the odds, 47 through, 47 through 53, any of those odds, they're all at CalcChat, none of them at CalcView. And then 55 is sort of an exploration thing. 57 is maybe a more practical problem, volume of a storage shed. Then I'd say do any of the odds, either 59 or 61. Now, if you're really into astronomy type stuff, the oblateness of Saturn is an interesting problem, but it's looks like it's a little involved. Okay, so if you wanted to try that, you certainly could. All right, any questions on 7.3? Let's move to 7.4. All right. Discard again. All right. 7.4. It'll sound like we did a lot today, 7.2 to 7.4, but we just did the last little bit of 7.2, all of 7.3, and then just get started in 7.4. I'm getting so hungry. Nothing since breakfast early this morning, around 6:30. So didn't get a chance for a snack or anything in between classes because I had the Okay, why am I sitting here talking? Why am I not going on with this? Okay. Again, applications of integration. This time we're going to look at arc length and surfaces of revolution. Not volumes, surfaces. Okay? Well, what do we mean by an arc length? Well, you know, a lot of our functions are sort of curvy type functions, right? What is the length of that curve? Yeah, I can do the length of a line, but the length of the curve is a lot more difficult. And that's what finding arc length is all about. Finding the arc length of a smooth curve. Notice there's a smooth curve. No points, cusp, or other things in it. You still can do those, but they're just messier. And then we're going to take that smooth curve and revolve that around a thing just like we did, but not look for the volume, but look at the surface area of that revolution, which means taking that curve and measuring how it integrates going around a 2 pi, So let's start with arc length. Definite integrals are used to find arc lengths of curves and areas of surface revolution. That's why it's under applications of integration. We're doing integrals. In either case, an arc or some segment of a curve is approximated by a line. We said we could figure out the length of a line. Curves are a little bit harder. So we're going to approximate it by the length of a line. And that length is the famous distance formula. Okay? If you know 2 points on a line, x1, y1, x2, y2, draw a straight line between them. What's the distance? So the length of that line, the square root of x2 minus x1 squared plus y2 minus y1 squared. Where does that come from? Pythagorean theorem. Where else do most things come from? If you think of x2 minus x1, that would be the horizontal section of that. y2 minus y1 is the vertical section. We're looking for this, and that would be c squared is equal to a squared plus b squared. And then c would be the square root of a squared plus b squared. Yeah, that's just straight out of Pythagorean theorem. Okay? Now, a rectifiable curve, I don't think I've ever used that word before. Okay? Taught from several different books before, but they've never used rectifiable. Curve is one that has a finite arc length. Okay? Only way I could think of an infinite arc length is one that had a vertical asymptote and it just kept going and going and going. Well, we're not going to do that. We're not going to go there. We're going to go finite arc length. Okay? So I guess these are rectifiable curves. You will see that a sufficient condition for the graph of a function f to be rectifiable between a f of a, that's xy, okay, and b f of b, that's that xy, is that the f prime, the first derivative, be continuous on the closed interval a to b. Such a function is continuously differentiable on a to b, and its graph on the interval a to b is a smooth curve. So to be continuously differentiable, that means it has to be a smooth curve. No corners, no cusp, no angles, they have to be smooth and continuous. Continuously differentiable. All right. So here's a function. Y is equal to f of x. Continuously differentiable on the interval a to b. So we'll call this point A and this our point B. Now, they don't have to be nice, symmetric, anything else. They could be anywhere. That could be A, that could be B. I mean, anywhere. It could be A down here and B up here. I mean, anywhere there. Okay? All it takes is in between there, nice, smooth, continuous curve. Okay? That is continuously differentiable on that interval a to b. You can approximate the graph of f by n line segments whose endpoints are determined by the partition. A is equal to x0, then that's less than x1, less than x2, less than x, up to x to the n, and finally to b. Now they don't have to be evenly spaced. Later we will, for safety purposes or thing. So you see, I'm going to leave this red in here. That would be the line segment. The curve's a little bit longer. That would be the line segment. The curve's a little bit longer. That would be, that's supposed to be a line segment, not a wiggle segment. And certainly the curve's a little bit longer. Okay? So you see, the smaller the thing here, the interval here, the closer you get. So this jumped from 2 to n, so I could have put several others in there. And they do sort of evenly space them, so you could have gotten one more in there. And that would have been a nice approximation. But you're not quite there. I mean, that underestimates always. How do you get the actual length up? What's the procedure? Smaller and smaller segments. And then you'll have, in your sound effects, almost have a good fit there. We'll keep getting smaller and smaller until you get infinitesimal. dx, not delta x. Okay? So, let's see if we can figure out how that will work then. By letting your delta xi be x of I minus x of I minus 1, delta y being y1, yi minus yi minus 1, you can approximate the length of the graph. This will be approximately the length. This is the arc length. Approximately the summation from 1 to n, however many of those little n's you have. The square root, this is our good old, this is formula. X of I minus 1 squared plus y sub I minus y sub I minus 1 squared. That would be your little s of I squared, you might say. We're going to sum this from I to n. You have n little divisions. You're going to do this for every one of them. Well, you can call that delta x of I squared minus plus delta x of y sub I squared. Okay? Is that really all that helpful? Well, maybe. If you divide, well, here's a trick. Okay? Nothing but a shell game maneuver here. Okay? It's a trick. What we're going to do is on this one, multiply and divide by x of I squared. All right? Delta x of I squared. Okay? Now factor out delta x of I, and I would have put this in front. The square root of delta x of I squared would be your delta x of I. I would have put it up here, though later we won't want it over there. But what do we have here? The square root of 1 minus delta x of I over delta x of I squared, all in the square root here. What does that become as you get smaller and smaller delta x, and therefore smaller and smaller delta y's? Change the deltas to d's, and suddenly you have dy dx. So that approximation becomes better and better as your intervals on the delta become very much smaller, meaning your n's are going to infinity. You're getting closer and closer to the actual curve there, and change that summation to an integration. The delta x, which you want at the end, is now a dx. And what do you have? That s with the limit is the delta is going to 0. Of course, the n's are going to infinity. The summation of 1 n equal to n, the square root of 1 plus delta y sub I over delta x of I squared times your delta x outside the radical there. This is what that is. The x prime f of x exists for every x in that interval. That's what we assumed to begin with. The mean value theorem guarantees the existence of c sub I, some center value in that interval, such that that is indeed going to be your derivative. Okay? This thing right here is delta y sub I is delta x, f of x of I minus f of x of I minus 1 from the very beginning. Delta x is going to be this. So this thing becomes your f prime of c. So this thing becomes this, becomes that. That's f prime. They're going sort of backwards and forwards all here. That becomes f prime. Okay? But it's squared. Okay? So here's your formula. The f prime is continuous. It follows that the square root of 1 plus f prime squared is also continuous and therefore integrable on a to b, which implies that this thing, your arc length, is going to become not a summation but an integral from a to b of square root of 1 plus f prime of x squared. Now, times dx. That is called the arc length between A and B. Now, notice they said, therefore, integrable. That doesn't mean that it's going to be easily integrable. Okay, they left off the easily for a reason. It's not. Just think of this. You've got to come up with a function in order to be easily integrable that when you take the derivative of that function, which you have to do here, and then square that derivative, which you do here, add 1 to it, that gives you something you can take the square root of and then integrate. Not any old function is going to work that nicely. So in reality, when you're doing these, most of the time you're going to be doing numerical integrations. You're going to buy a package and do the integration, which most of you are becoming engineers, right? Maybe not all, but most. You're going to try to have packages do as much as you can for you. You're not going to be doing these integrations by hand necessarily. You may some, and you need to know how to think through them, but in reality, you're going to be using programs to do this, packages to do this, okay? So here's the definition of arc length. Let some function y is equal to f of x, and those have to be, in order to do these by hand, have to be very carefully selected f of x, represent a smooth curve on some interval a to b. The arc length of f between a and b is then this, s is the arc length, equal to integral from a to b, makes sense, of the square root of 1 plus f prime squared dx. Delta x became a dx, and this became f prime squared. Now, in order to do that integral, you have to have a function here whose derivative squared with 1 added to it. You can take a square root of it, or integrate it with a square root in there, and come up with something cool. Okay? Now, similarly for a smooth curve, x is equal to g of y, the arc length of that one, and this is going from y equals c to y equals d. That would then be the integral from c to d of the square root of 1 plus g prime of y. So this is dg dy squared times dy. Okay, that would give you the arc length if you're doing what I think of as vertically defined functions as opposed to horizontally defined functions. Okay, here's example 1. You think we have time to do it. Oh, this won't be bad at all, will it? This is something quite doable. Okay, find the arc length from x1, y1 to x2, y2 on the graph of f of x is equal to mx plus b. Okay, what's one of the first things you got to do? If you remember your function, the arc length is the integral from, this would be from x1 to x2, right, of mx plus b. Whoa. Let me keep it more generic than that. Okay. Integral of the square root of 1 plus f prime of x squared dx. Okay? There's your f. Okay? So what's the first thing you're going to have to do before you can even start your integration? Hint, you don't see f anywhere in that function, in that integral, right? What do you see in there? You see an f? F prime. So the first thing you got to do is do f prime of x. And what's f prime of x? Is f of x is mx plus b. Help me. Second? M, and that's all, folks, okay? Okay, so yeah, your f prime. What's the next thing you do with that? You square it. So what's the square of that? M squared, right? Pretty hard, right? And then what's the next thing you do to it? Add 1 to it. Okay, we've done that. Then you take the square root of that. So you're doing, the arc length is equal to the integral from x1 to x2 of the square root of m squared plus 1 dx. Okay? I don't really like the way that looks. Do you? Let's change that from x1 to x2 of m squared plus 1 to the 1/2. Whoa! Got dx. Okay. Well, wait. Who cares? This is not going well. That's just a constant, isn't it? M is something you know from your problem. There's no x's in there, so that is simply I thought this was going to be easier than it's turned out being. You know what they're doing, and we don't have time for it. They go back and give you what M is. So let's hang off of this. Let's start again next time, afresh from example 1. And since we didn't get an example done, no new homework exercises in 7.4. We'll go from there. Sorry. It is pretty easy, but you can't just do it from here. You have to go back and do some other.